Welcome to Late Night History. Settle in. Let your shoulders drop. Let the pillow take the whole weight of your head. And let me tell you a story about the ground beneath you. The ground you have trusted without a single thought every day of your life. It has held your bed. It has held every bed you have ever slept in. It feels like the one thing in the world that does not move. And tonight, very slowly, in a voice you can drift off inside of, I am going to tell you that it does move, not the way you think, not the way you have already heard, but in a second, hidden way that almost nobody feels and almost nobody knows. Picture the whole Earth for a moment. Not a map, not a globe on a shelf, but the real thing, a sphere of rock nearly 13,000 kilometers across, turning once a day, wrapped in its thin skin of oceans and continents. Now imagine that the entire solid body of it, the crust you stand on, and the deep hot mantle beneath, all of it together as one single piece, very slowly begins to roll. Not spin faster, not tip over in some violent lurch, just roll, gently, over the course of millions of years, so that a place that once sat under the warm belt of the tropics drifts over unimaginable time to lie nearer one of the poles. The palm-warm equator of some ancient age creeps toward the cold. And the strange part, the part that takes a moment to sink in, is that the continents do not rearrange themselves to do this. They stay exactly where they are, relative to one another. The same oceans lie between the same shores. The whole map holds its shape perfectly, and yet the entire map, the entire planet, quietly rotates itself into a new position underneath its own spinning. The rock reorients. The world tips inside its own turning. Scientists have a name for this. They call it true polar wander. And the first thing to understand, the thing to hold on to as you sink deeper into the quiet, is that this is not the drifting of continents. You have heard of that one. Everybody has heard of that one. The slow shuffle of the plates. Africa easing away from South America, the Atlantic widening a few centimeters a year, the map of the world redrawing itself over hundreds of millions of years. That is real, and that is a different story. True polar wander is something else entirely, something rarer and stranger, and one of the quiet pleasures of tonight will be keeping the two of them cleanly apart in your mind, like two lamps in two different rooms. But before we go any further into what it is, let me hand you the strangest thing about it, the thing that, when I first understood it, kept me awake in exactly the way I hope tonight will help you fall asleep. Somewhere in the mountains of central Italy, in the folded green ridges of the Apennines, there is a kind of stone. It is a limestone, pale and fine-grained, and where it is freshest, it carries a soft pinkish blush, the colour of the inside of a shell, or of the sky just after the sun has gone. Geologists call it the Scaglia Rossa, the red flake, the red scale, and it was laid down at the bottom of an ancient sea, grain by grain, drifting shell by drifting shell, over millions of quiet years in the age of the dinosaurs. It is old. The particular layers that matter to our story formed somewhere between about 86 and 78 million years ago, in the late part of the Cretaceous, when the great reptiles still walked and the world had a very different shape. And this stone remembers something. It remembers which way was north. Not north as in a place, north as in a direction. The direction the Earth's magnetic field was pointing, right there, at that spot, 84 million years ago, when the mud that would become this limestone was still soft and settling on a dark sea floor. The stone locked that direction in. It froze it, the way a photograph freezes a face, and it has held it ever since, through the extinction of the dinosaurs, through the rise of the mountains that now carry it, through every sunrise of the last 84 million years, a fossil compass sealed in rock, its needle pointing forever at a pole that no longer sits where it did. And when geologists read that frozen needle, layer by patient layer, going up through the stone the way you might turn slowly through the pages of a diary, they found something that should not have been there. They found a record of the whole planet tilting. The frozen compass, page after page, showed the pole swinging away by about 12 degrees, and then, over the next few million years, swinging back again, out and then home. A great slow lean of the entire Earth, and then a great slow recovery, all of it written down in pink stone by a sea that has been gone for longer than there have been mountains in Italy. The researchers who found it gave it a name that I love, because it is so gentle and so playful for something so enormous. They called it a cosmic yo-yo, the planet tipping out and rolling back, like a yo-yo easing down to the end of its string and climbing calmly home to the hand. 12 degrees is not a small thing when the thing that is tilting is the entire solid Earth. Though I will tell you honestly, more than once tonight, that scientists still argue about exactly how far the planet has swung in its deepest past. And I will not pretend those arguments are settled. But this one, this pink limestone yo-yo of 84 million years ago, is among the better-behaved pieces of evidence, one of the more tightly held. The stone seems fairly sure of what it saw. So that is where we are going tonight, slowly down into a single strange and beautiful idea that the whole Earth once rolled over, gently. And that we know because an ordinary slab of pink Italian rock kept an honest magnetic diary and never lost the page. Before we go further down, let me do the small human thing I always like to do at the start of one of these long nights. I would love to know where in the world you are listening from. It is a strange and lovely thought, that this same quiet story is soaking into the dark in so many different places at once, someone under a city window with the traffic hushed below, someone in a farmhouse with the fields black and still outside, someone very far away where it is not even night at all. If you feel like it, and it costs you nothing, leave a word in the comments telling me where you are. I read them. It makes the vastness of a subject like this one feel a little less lonely, a little more shared. And if you are new here, and you would like more of these slow, careful journeys into the old and the unexplained, the kind you can fall asleep inside of without missing anything essential, then quietly subscribe. And there will always be another one waiting for you in the dark. There is no rush. There is nothing you need to do. You can close your eyes right now and simply let the words carry you. The story will keep going whether you are awake for all of it or not, and that is exactly how it is meant to be. Now, let me set the idea properly, because it rewards a little patience, and because the more clearly you can picture it, the more easily the wonder of it can settle over you like a heavy blanket. Hold the Earth in your mind again. It is spinning. It has always been spinning, in the sense that matters to us, turning once a day about an invisible line that runs through it, through the North Pole, down through the deep core, out through the South Pole. That line is the spin axis, and here is the first thing that surprises almost everyone. The first small door into the mystery, that line, that axis, does not really move. Out in space, relative to the distant stars, the direction the Earth's axis points stays essentially fixed. It is held in place by something physicists call angular momentum, the same stubbornness that keeps a spinning top pointing the same way, or a bicycle wheel upright as long as it is turning, or a figure skater's spin steady and true. A spinning thing resists having its axis shoved around. The Earth is an enormous spinning thing, and so its axis, out in the great dark, holds its aim with tremendous constancy. So if the axis in space does not move, then what, exactly, is doing the moving? What tips? What rolls? What is it that carries a tropical seafloor slowly poleward if the very line the planet turns about is standing still? That is the master question of the whole night, and I am going to let it hang open for a good long while, the way you might leave a door ajar in a warm house so you can hear the rain outside without getting wet. Hold the question loosely. We will return to it and answer it fully, and the answer will make a certain deep sense that you can almost feel in your body. But first let the strangeness of it work on you. The axis is fixed. Something still moves. Both are true. The resolution, when it comes, is this, and I will only sketch it lightly now and fill it in properly later when you are further down toward sleep. The spin axis is a line in space, but the solid body of the Earth is a separate thing from that line. The rock is not welded to the axis. The rock can slide around underneath it, can reposition itself, can bring a different part of its surface up to sit beneath the fixed pole in the sky. Imagine you are holding an orange with a knitting needle pushed straight through it, top to bottom, and the needle is clamped in a vise so it cannot move. The needle is the spin axis, fixed. Now imagine the flesh of the orange is soft enough that, very slowly, over a long time, you could rotate the peel and the pulp around inside, sliding the fruit around the needle without moving the needle at all. The point that was at the top drifts down toward the side. A freckle on the peel that started at the pole ends up nearer the equator. The needle never budged. The orange rolled around it. That, more or less, is true polar wander. The solid earth, the whole shell of crust, and the deep mantle beneath, all together as one coherent body, very slowly repositioning itself around a spin axis that stays put in space. The planet rolls, the axis holds, and a place that was polar becomes tropical, or a place that was tropical becomes polar, not because it packed up and travelled there under its own steam, but because the entire world quietly turned underneath the pole and brought that place to a new latitude. I want to sit here for a moment, because this is where true polar wander and continental drift are so easily confused, and keeping them apart is the single clearest gift I can give you tonight. So let us light both lamps and look at them side by side, gently. Continental drift. Plate tectonics, to give it its proper modern name, is the story of pieces. The Earth's rigid outer skin is broken into a set of great plates, like the cracked shell of a boiled egg, and each of those plates moves independently, on its own, in its own direction, sliding over the softer, warmer layer beneath. One plate creeps north, while its neighbour creeps east. They pull apart at the mid-ocean ridges, where new seafloor wells up, and they grind together at their edges, where mountains rise and earthquakes shudder, and old seafloor plunges back down into the depths. It is a story of many parts moving separately, each dragged along by the sinking of cold, heavy slabs at its far edge, and nudged by the upwelling at the ridges. Africa goes one way. The Pacific Plate goes another. The map is a mosaic, and every tile drifts on its own. True polar wander is not a story of pieces at all. It is a story of the whole. In true polar wander, nothing slides independently. Every plate, every continent, every ocean basin moves together all at once in the same rotational sweep, as if the entire outer world had been frozen into a single rigid ball and that whole ball were rolled a little way. The mosaic does not rearrange, the tiles keep their pattern exactly. It is the whole picture, frame and all, that turns, and that gives it a signature, a fingerprint that geologists can look for. Because in true polar wonder, every point on Earth swings in the same rotational sense at the same time, all of them turning about one common axis that lies out on the equator. It is a single coherent planet-wide roll. Continental drift scatters, true polar wonder sweeps. There is one more thing under that same roof, and I mention it only to lock the door against it, because it is the third thing people so often muddle in with the other two, and I do not want it wandering into your dreams tonight, pretending to be something it is not. That third thing is a magnetic reversal, the times, scattered through Earth's history, when the magnetic field itself flips, so that a compass that pointed north would come to point south. That too is real. That too is a different story. When the field reverses, the rock does not move and the planet does not roll, only the invisible magnetism swaps its ends. Three separate phenomena then, and I will keep them separate all night. Continental drift, where the plates move independently, magnetic reversal, where the field flips its polarity, and true polar wonder, our subject, the strangest of the three, where the entire solid Earth rolls as one over its own fixed spin. Hold those three lamps apart in three different rooms, and the whole story stays clear even as you grow drowsy. Now, you might reasonably wonder, half asleep, how anyone could ever catch the whole Earth in the act of such a thing. It is so slow, it is so vast. There were no witnesses 84 million years ago. There were only dinosaurs and drifting shells and a dark, warm sea settling its mud a grain at a time. How on earth, the phrase has never been more literal, could we possibly know? And the answer brings us back to that pink limestone in Italy, and to the quiet miracle that makes this entire field of knowledge possible. Certain rocks keep a magnetic memory. They are honest little recorders, and they have been recording all along, whether or not anyone was ever going to read them. I will save the full mechanism for a little later, when we go down into it properly, but let me give you the shape of it now, softly, as something to turn over as you drift. Deep in many rocks there are tiny grains of iron-bearing minerals, grains of magnetite, chiefly, a common iron oxide, and its cousin hematite. And these grains are, in effect, minuscule compass needles. When the rock is hot, when it is molten lava, say, pouring out and beginning to cool, or when it is soft sediment still settling on a sea floor, those little grains are free. They can turn. They can align themselves with the Earth's magnetic field, pointing the way the field points at that place, at that instant. And then the rock cools, or the sediment compacts and hardens, and the grains are locked, frozen in place, fixed forever, or near enough to forever, pointing in the direction the field was pointing on the day the stone was born. A compass that took one reading ages ago and then could never move again. That is why the Scaglia Rossa can remember which way was north 84 million years ago. It is not a metaphor, it is iron. Countless microscopic iron compasses, sealed in pink stone, all still faithfully pointing at a pole from the age of the dinosaurs, a pole that, thanks to the slow roll of the whole planet, is not where it used to be. And when you read those frozen needles carefully, and you find that as you climb up through the layers the direction they point swings away and then swings back, you are watching, in stone, the Earth itself tilt out 12 degrees and roll home. You are holding the yo-yo's whole journey in your hands. There is even more that the frozen compass gives us, and this is the part that turns a curiosity into a real science, so let me lay it beside you as gently as I can. It is not only the horizontal direction, the which way is north, that the rock records. It also records the tilt of the needle, how steeply it dips down into the ground. And that dip, that downward tilt of the frozen magnetic needle, quietly reveals the latitude at which the rock was born. How far it sat from the equator. Whether it formed in the tropics or halfway to the pole or somewhere at the cold ends of the world. The reason is a lovely piece of geometry, and you do not need to hold on to the arithmetic, only the picture. Earth's magnetic field, taken in the large and over long spans of time, behaves roughly like a simple bar magnet sitting at the center of the planet, lined up with the axis. Near the equator, the field lines run nearly flat, parallel to the ground. And so a compass needle free to tilt would lie almost level, its dip near zero. But as you travel toward a pole, the field lines curve down and plunge into the earth, and the needle tilts down to follow them, steeper and steeper, until right at the magnetic pole itself, the needle points essentially straight down, standing on its nose. Flat at the equator, vertical at the pole, and every latitude in between has its own particular in-between angle, its own signature tilt. So when the geologist measures the frozen dip in a grain of ancient magnetite and finds, say, a shallow, near-level tilt, the stone is telling them, I was born near the equator. And a steep, plunging tilt says, I was born far from it, up toward the cold. The rock records not only its old direction, but its old distance from the middle of the world, its old latitude, printed in iron. Do you see, then, how the whole thing hangs together? If a slab of limestone that we know formed in one fixed place, because the continent it sits on has not drifted very far in the meantime, and we can account for the drift it did do, nonetheless shows its frozen latitude shifting, swinging the rock poleward and then back toward the tropics over a few million years, without the continent itself having gone on any such journey, then something else must have carried it. Something must have moved that patch of the world to a new latitude and then returned it, without dragging its neighbours out of arrangement. And the only thing that can do that, the only thing that moves every place at once while keeping the whole map intact, is the roll of the entire solid Earth about its fixed spin axis. True polar wonder. The stone felt the planet tip, and it wrote it down. That is the detective story we are inside of tonight. A fossil compass in Italian limestone, catching the whole Earth in a slow 12-degree lean 80 4 million years ago. A lean out and a lean home. And behind it, as we will find in the hours ahead, a culprit hiding 2,900 kilometers beneath your feet. A deep, lopsided, off-center world quietly trying to rebalance itself, the way a spinning thing always does. But I am getting ahead of the slow pace I promised you, and there is no need to hurry toward the answer. That is the whole gift of a night like this. You are allowed to fall asleep before the ending. You are allowed to drift off somewhere in the middle of the mystery and never learn how it comes out, and that is not a loss, because the not knowing is soft here, not sharp. There is no cliff you will fall off of. There is only a very old, very large, very gentle fact that the world you are lying on has, in its long life, rolled over and rolled back, being turned slowly in the dark, the way you might turn a smooth stone over and over in your hand until your eyes close. Let me leave you, for now, with the open door I promised to leave open. The spin axis, out in space, does not move. It is held fixed by the great steadiness of a spinning world. And yet the solid Earth moves anyway, rolling around that fixed line, carrying tropics toward the poles and back again over the slow arithmetic of millions of years. Two things that seem to contradict each other, both entirely true. The needle in space, standing still, the orange turning around the needle. So what is it, really, that does the turning? What reaches into the whole vast body of the planet and eases it around so patiently that no creature alive has ever felt a moment of it, and yet so surely that the pink stones of Italy caught the whole event and kept it safe for 84 million years? What could possibly be strong enough and lopsided enough and old enough to roll the entire Earth? Hold that question loosely as you breathe out. We are going to follow it all the way down through the frozen compasses in the rock, down through the patient scientists who first caught the planet leaning, down through the 21-kilometer bulge around the Earth's own waist that both steadies the world and, ever so slowly, lets it move, and down at last to the two vast shapes lying against the core in the deep dark, larger than continents, that may be the quiet hands doing the turning. But not yet. For now, there is only the pink stone and the fixed star of the axis and the slow, certain, harmless truth that the ground beneath your bed has rolled before and may be rolling now, too gently for you ever to feel. Let that be a comfort rather than a worry. The Earth has been doing this calmly since long before there was anyone to notice, and it will go on doing it long after tonight. It is in no hurry at all. And neither, right now, are you. Before we go down, though, let me ask you something, quietly, the way you might ask a friend lying awake in the next room. Where in the world are you tonight? What ground is under your house, under your city, under the streets you walked today, without a single thought for how far they have travelled? Somewhere warm, somewhere cold, somewhere the sun has only just set or is only just about to rise. I would genuinely like to know. If you feel moved to, leave it in the comments before you drift off. A single word, a place name, a pin dropped somewhere on this old turning world. And if you find that this slow kind of story is the one that finally loosens the knot in your mind at the end of the day, then stay a while, subscribe, and there will be more of them waiting for you every night, unhurried, the same calm voice walking you down into something ancient and strange, and in the end, oddly soothing. That is all. The invitation is made. Now let us forget the room entirely and go into the Earth. Here is the first thing to settle, because it is the thing almost everyone gets wrong, and getting it right is what makes the rest of the night make sense. What we are describing is not the continents drifting. It is easy to hear the land moved and picture the map you already half remember. The coastlines of Africa and South America fitting together like two torn halves of the same page. The slow separation of oceans, the crawl of India up into the underside of Asia to heave the Himalayas into the sky. That is real. That is continental drift, plate tectonics, and it is a magnificent story of its own. But it is not this story. It is, in fact, almost the opposite of this story, and the difference is the whole point. In plate tectonics, the outer skin of the Earth is broken into pieces, great rigid plates of rock, each one drifting on its own, sliding independently over the hotter, softer layer beneath, the asthenosphere. One plate is dragged down into the depths by the cold weight of its own sinking edge. Another is pushed apart at a ridge where new rock wells up, and each goes its own separate way, at its own separate speed, in its own separate direction. It is a raft of broken ice on a slow river, each floe turning and parting from its neighbours. That is drift. Pieces, moving with respect to each other. What we are following tonight is something else entirely. Imagine, instead of the broken pieces, that the whole shell of the Earth moves as one. Not the plates sliding past one another, but the entire outer body of the planet, the crust and the vast deep mantle beneath it all together, rolling as a single coherent thing over the liquid core at its heart. Nothing rearranges. The continents keep their exact places relative to one another. The Atlantic does not widen. India does not press any harder into Asia. The map you know stays the map you know. And yet the whole of that unchanged map rotates bodily across the face of the world, so that a place which sat squarely on the equator, drenched in tropical sun, is carried slowly, coherently, without ever losing its neighbours, toward one of the poles. Every plate moves the same way at once, all of them together, turning about one shared line. That is the signature, the fingerprint that tells the two apart. Drift scatters, this gathers, this turns the whole orange, while every seed inside it stays exactly where it was. Scientists have a name for it, a plain and rather beautiful name. They call it true polar wander. True, to mark it out from the merely apparent wandering that the drifting continents can fake. Polar, because it is the poles that a given patch of ground seems to travel toward or away from. And wander, for the slow, patient, aimless-looking way the solid earth roams beneath its own fixed spin. True polar wander. Say it once, softly, and then let it go. You do not need to hold it. It will still be here when you wake. And now we come back to the riddle we left hanging in the dark, because naming the thing has only sharpened it. If the continents are not rearranging, and the spin axis out in space does not move, its ends still pointing at the same distant stars they pointed at when the dinosaurs walked, then what, in the name of everything, is doing the turning? Something must be. The pink limestone in the hills of Italy is not lying. Its frozen needles record a north that has since swung 12 degrees away and 12 degrees back, and a rock cannot invent such a thing. So the motion is real. The axis is fixed. The continents keep their formation. And still, somehow, the entire solid earth has leaned over and righted itself again, like a great ship taking a long, slow swell and settling back onto its keel. That is the mystery, laid bare and whole. Not a mystery of missing evidence, for the evidence is written plainly in the stone. A mystery of cause, of what hidden hand, buried somewhere in the miles of rock beneath us, is heavy enough and patient enough and lopsided enough to take hold of the whole planet and ease it around its own unmoving axis, so slowly that 100 generations of living things could come and go without a single one of them feeling the floor so much as tremble. Something down there is out of balance. Something is pulling the earth gently off true and then coaxing it back. And to find out what, we will have to leave the surface behind and follow the frozen compasses down into the rock and learn first how it is that a stone can remember anything at all. Begin then with the question that the stone itself was built to answer. How does rock remember? Not in the way we think of memory as something chosen and kept, something deliberate. Rock does not decide to preserve the past. It simply obeys the laws of physics with a patience that embarrasses every other kind of record-keeping we have ever invented. It does not fade like ink. It does not rot like wood. It does not blur like the memory of a human mind waking from a dream and finding the edges already softening. Rock records because it cannot help it. The physics takes hold, and the record is made whether anyone is watching or not, and it will still be there 200 million years later, waiting for someone patient enough to go looking. The mechanism begins with heat, as so many things in geology do. Imagine a volcano. Not the cinematic kind, not the dramatic wall of orange pouring down a hillside in fast motion, though that too is real. Imagine instead the quieter truth of it, molten rock pushing up through the crust, finding a path, cooling. The cooling is the thing. The cooling is where the record is made. As magma rises and meets the cooler world above, it begins to lose its heat, degree by degree, and as it does, the minerals crystallizing out of the melt begin to take their final forms. Among those minerals, scattered through the cooling rock in grains too small to see without a lens, is magnetite. Iron oxide, specifically, a mineral whose chemical name is 5304. Which is simply the notation for a molecule built from one iron atom paired with another, and then a third, all bound to 4 oxygen atoms in a structure that, at certain temperatures, is powerfully responsive to the presence of a magnetic field. At high temperatures, the kind that belong to molten rock, the magnetic domains inside each magnetite grain are in constant agitation. Thermal energy is enough to flip them continuously, randomly, back and forth, so that the grains as a population point in every direction at once, their signals cancelling, producing no net alignment. The rock is magnetically disordered, even as it crystallizes. But as cooling continues, there comes a temperature at which the thermal agitation can no longer overpower the energy needed to keep flipping the magnetic domains. The grains lock. They settle into whatever direction the ambient magnetic field is pointing at that moment, and they stay there. For magnetite, that critical temperature sits at roughly 580 degrees Celsius. For hematite, another iron oxide whose formula is Fe2O3, the locking temperature is a little higher, closer to 680 degrees. These temperatures have their own name in geophysics, the Curie temperature, after Pierre Curie, who first established the relationship between heat and magnetic order, and the Knell temperature for certain other minerals. But the principle is the same in every case: cool past the threshold, and the record is sealed. The name for this kind of magnetization, the kind baked permanently into a rock as it cools through its Curie temperature, is thermoremnant magnetization. Thermo, because heat is the mechanism. Remnant, from the Latin for remaining. Because the magnetization remains after the field that produced it is gone. If you could somehow remove the Earth's magnetic field entirely after the lava had cooled, the rock would still carry the direction it had locked in. The field imprinted itself and departed, and the rock held the imprint. It is the most faithful kind of recorder nature has found, no mechanism for the memory to drift. No chemical pathway by which the alignment slowly unwinds, just the orientation of iron grains held in a mineral lattice that may last, in the right geological circumstances, for hundreds of millions of years. Sedimentary rock keeps a different but closely related kind of record. Imagine a lake or an ancient seafloor, or any quiet body of water where small particles are settling through the water column, drifting down from the sunlit surface toward the mud below. Among those particles are tiny grains of magnetite eroded from older rocks upstream, worn to dust and carried by rivers to their eventual resting place. As each grain falls slowly through the water, it behaves exactly as a compass needle behaves in air, it aligns itself with the ambient magnetic field. It spins as it falls, orientating its long axis, finding the direction the field is pointing, and by the time it settles into the sediment and is buried by subsequent layers, it is frozen in that orientation. Not by heat this time, but by the physical binding of burial and compaction. This is detrital remnant magnetization, the compass needle arriving not by crystallization, but by sedimentation, settling into alignment before the sediment hardens around it and makes the record permanent. Both mechanisms, the thermoremnant and the detrital, produce the same kind of information. They record the direction of the Earth's magnetic field as it existed at the place and time the rock was formed, which is where the extraordinary utility of this begins to come into focus, because the Earth's magnetic field is not uniform. It does not point in the same direction everywhere on the surface, and it is not equally steep everywhere either. These two things, direction and steepness, are the twin handles by which the frozen compass in the rock allows us, reading it thousands or millions of years later, to reconstruct where the rock once sat on the globe. The steepness has the simpler story. Think of a compass needle, not the flat horizontal kind familiar from hiking, but a compass needle free to tilt in 3 dimensions, balanced on a pivot, so it can point not just north, but also up or down. Such a device is called an inclinometer, and if you carried one around the Earth, you would notice something systematic and beautiful happening. At the equator, the needle lies flat. It has no inclination, no preference for up or down, because at the magnetic equator the field lines of the Earth's dipole are horizontal, running parallel to the surface. As you walk north or south away from the equator, the needle begins to dip, it tilts toward the ground. The closer you get to the poles, the steeper the tilt becomes, until at the magnetic poles themselves the needle points straight down, perpendicular to the surface, chasing a field line that is diving directly into the Earth. This relationship between the angle of dip and the latitude has a precise mathematical form. The tangent of the inclination angle is equal to 2 times the tangent of the latitude. It is written tan I equals 2 times tan of the latitude, and it holds with enough fidelity that measuring the inclination of the frozen magnetic field in a rock, reading the angle at which the ancient compass needle is preserved in the stone, directly yields the latitude at which that rock formed. Not approximately, not roughly, to within a few degrees, depending on the quality of the preservation and the number of samples taken. The stone carries its latitude like a fact about itself, a physical inscription made the moment it cooled or settled, impossible to alter after the fact, waiting to be read by anyone with a magnetometer and the knowledge of what to look for. This is the key to everything that follows, so it is worth letting it settle before moving on. A piece of basalt from a lava flow that erupted 84 million years ago carries, locked inside its magnetite grains, the precise steepness at which the magnetic field was pointing on the day the rock cooled. That steepness translates into a paleolatitude, a fossil latitude, the latitude where the rock was sitting when it formed. And because paleolatitudes from different rocks and different ages can be compared and assembled into a sequence, geologists can trace the path a given piece of crust has travelled through latitude over geological time. Not all of that motion is true polar wander. Some of it is ordinary plate tectonics, the continent carrying the rock north or south as it drifts. But some of it is something else, something deeper, and separating the two is the detective story that took decades to work out. The second handle, the declination, the horizontal direction in which the frozen needle points, tells a different but complementary part of the story. A rock preserving a declination that points not toward the modern geographic north, but toward some other direction, has rotated since it formed. Its whole tectonic block has spun, or the region in which it sits has twisted, or some other process has turned the rock body away from its original orientation. Declination is the record of rotation, just as inclination is the record of latitude. Together, inclination and declination allow a geologist to compute not merely where in latitude a rock once sat, but also to construct what is called an apparent polar wander path, a track that shows where the magnetic pole appeared to be, as seen from the continent that holds the rock, at each successive moment in geological time. The phrase is carefully chosen. Apparent polar wander, not actual. Apparent, because the path of the pole relative to a given continent depends on both where the pole actually was and where the continent was. If the continent drifted, the pole appears to move even if it did not. If the pole moved but the continent stayed fixed, it also appears to move, and if both moved, the apparent path is the combined signal of both motions tangled together, waiting to be untangled. Quick reminder, after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. The untangling, when it finally came, was one of the more elegant revelations in the history of Earth science. And it came not from any single experiment or any single piece of rock, but from the accumulation, over years and then decades, of paleomagnetic measurements from dozens of locations around the world, from many different continents, all being assembled and compared at roughly the same time in the middle of the 20th century, when the analytical tools and the patience to apply them were finally both available together. Among the people doing that work were Keith Runcorn, a British geophysicist who spent much of his career at Cambridge and later at Newcastle, Edward Irving, a Canadian scientist whose work on the paleomagnetism of Indian and Australian rocks proved particularly decisive, and P.M.S. Blackett, a Nobel laureate who had turned his attention from particle physics to the Earth's magnetic field with a rigour that the field badly needed. Together, and in parallel with other workers around the world, they began amassing the apparent polar wander paths for different continents, the path the pole traced, as seen from Europe, the path it traced, as seen from North America, the path from India, from Australia, from Africa. If only the pole were wandering, and all the continents were fixed in place, then every continent would give the same path. The pole's track would look the same from everywhere, but that is not what they found. The paths diverged. Europe's apparent polar wander path and North America's were different. Not slightly different, not within the margin of measurement error, but dramatically, systematically different, in a way that had a clear geometric interpretation. The two paths had the shape they would have if the continents had once been together and had since moved apart. The Atlantic Ocean had opened between them, and in opening it had carried Europe one way and North America another, causing the pole to appear to have been in different places depending on which continent's rocks you were reading. This was one of the key pieces of evidence that eventually convinced the scientific community that continental drift was real. Not a geological fantasy, as many had considered Wegener's proposal to be, but a measurable, documented fact embedded in the rocks of every continent. The diverging apparent polar wander paths were the signature of separated landmasses, the electromagnetic ghost of a supercontinent pulled apart. But the story did not end there, because the diverging paths also implied something more. If you took the apparent polar wander paths of the different continents and reconstructed the positions of those continents as they had been in the geological past, sliding them back together as the paleomagnetic evidence suggested, and if you then looked at what path the poles seemed to trace when all those continents were returned to their ancient positions, you found that even after accounting for all the drift, there was still a residual motion left over, a common component that was not explained by any individual continent moving, a motion that all the continents seemed to share simultaneously, as if they had all been nudged in the same direction at the same time, all rotating together around a single common axis. That residual shared component is the signal. That is what true polar wander looks like from the inside, not any single continent moving relative to the others, but all of them moving together, coherently, because the entire shell they ride on, the whole mantle and crust system, has rotated as a unit. The individual plate motions cancel out when you look at the shared component. Only the true polar wander remains. To make the separation cleanly, however, you need a reference frame, a set of anchors fixed enough in the mantle that you can measure everything else's motion relative to them. Plate boundaries move, mountain ranges rise and are eroded. But deep beneath many of the ocean plates there are hotspots. Regions where especially hot material from deep in the mantle punches through the plate above, forming chains of volcanic islands as the plate slides over the stationary heat source. Hawaii is the most famous example. The chain of islands and seamounts stretching northwest across the Pacific is the track left by a plate moving over a deep mantle plume. Each island progressively older as you move away from the active Big Island where the hotspot currently sits. If you treat hotspots like Hawaii as roughly fixed pins hammered into the mantle, you can use the tracks they have burned through the overlying plates to reconstruct not just the plate's motions, but the motion of the mantle itself relative to the spin axis. Measure the ages and positions of the volcanic chain. Reconstruct where the hotspot was sitting at each moment. Compare that to where it should be sitting if the mantle were perfectly still. Any systematic, coherent rotation of all the hotspot tracks together, in the same sense, about the same equatorial axis, is the signature of the whole solid Earth having rolled. This is the hotspot reference frame, and it is the frame in which the true polar wander signal can be isolated most cleanly from the noise of ordinary plate motion. The picture that emerges from all of this, from the frozen inclinations, the divergent apparent polar wander paths, the shared residual component, the hotspot reference frame, is of a planet that is not as still as it appears. A planet that has, over the course of its long history, reoriented itself multiple times. Some reorientations modest, some perhaps large, all of them slow by human standards and yet geologically dramatic, readable in the stone if you know the language the stone is using. And the stone does not use a complicated language. It uses the simplest possible record, the direction a magnetic grain was pointing when it stopped being free to point in other directions. It uses physics that has not changed since the first magnetite grain crystallized in the first lava flow that ever cooled on this planet. The temperature at which magnetite locks its orientation is the same today as it was 500 million years ago. The relationship between inclination and latitude follows from the geometry of a dipole field, which also has not changed. The rock is not interpreting anything. It is not making a judgment or applying a model. It is simply obeying thermodynamics, and in doing so it preserves, with a fidelity that no human archive can match, the orientation of the Earth's magnetic field at one specific moment in one specific place. Which brings us back, inevitably, to the limestone, to the pink rock in the hills of Italy, laid down in deep water more than 80 million years ago, carrying inside it the record of what the field was doing when the seafloor sediment settled and compacted and became stone. The Scaglia Rossa is not an unusual rock in most respects. It is the kind of fine-grained pelagic limestone that forms in many parts of the world, built from the tiny calcium carbonate shells of organisms that lived and died in the water column and sank to the bottom in an unbroken, continuous rain over millions of years. What makes it unusual, what makes it the kind of rock that a paleomagnetist looks at with the particular attention a reader gives to a letter from a trusted friend, is the quality of its record. The sediment accumulated slowly and steadily. There is very little disturbance in the layers, and the detrital magnetic grains settled faithfully into alignment as they came to rest, layer by layer, year by year, preserving the field direction in what amounts to an almost unbroken diary covering many millions of years of geological time. When Ross Mitchell and Sarah Slotsnik and Joseph Kirschvink and their colleagues sampled the Scaglia Rossa, taking cores from outcrops in the Italian Apennines, carrying those cores to the laboratory, measuring their inclinations and declinations with the precision that modern instruments allow, what they found in the record spanning roughly 86 to 78 million years ago was not a steady signal. The inclinations changed. Not randomly, not noisily, but in a systematic pattern. The magnetic dip, which encodes the latitude, shifted in a direction that indicated the rock had moved to a higher latitude during a certain window of time, and then shifted back, returning to something close to its original value over the following few million years. The amplitude of that shift, when converted from inclination to latitude, came to roughly 12 degrees. 12 degrees of latitude is not a small thing. 12 degrees of latitude on a sphere the size of the Earth is more than 1,000 kilometers of displacement measured at the surface between whatever geographic point you choose to track and the position of the spin pole. If a tropical shoreline were to migrate 12 degrees closer to a pole, it would find itself in a very different climate. A very different world of storms and seasons and light. 12 degrees of latitude is the difference between the climate of the Caribbean and the climate of, say, Northern Virginia. It is enough to matter to every living thing on the surface. And then it came back. That is the thing the rock records with equal clarity. The inclination did not shift 12 degrees and stay there. It shifted outward, and then, over millions of years, it returned. The rock records not a permanent migration to a new position, but an oscillation, a leaning away and a settling back. A motion that the scientists who reported it in 2021 in the journal Nature Communications described with a phrase that has a certain lightness to it, a certain appropriately cosmic domesticity, a cosmic yo-yo. The planet swung away, and the planet swung back. And in the limestone of the Italian Apennines, each layer a year or a decade of quiet sediment laid down in an ancient sea that no longer exists. The record of that swinging is preserved with a clarity that 200 years ago no one would have thought possible to retrieve from the deep past, not because anyone at the time was looking or knew that such a record was being kept, but because the physics did not care whether anyone was watching. The grains settled. The field printed itself into them. The sediment hardened. The mountain range that would become the Apennines formed millions of years later, lifting the old seafloor into the hills where it now weathers and waits. And eventually, in the 21st century, a team of scientists with coring equipment and magnetometers and enough mathematical machinery to separate signal from noise walked up into those hills and read what the rock had been quietly holding all along. There is something worth dwelling on in that image before we move deeper into the question of why the planet tipped in the first place and what was heavy enough in the depths to pull it. The fossil compass in the rock is not a metaphor, it is a physical object, a grain of magnetite a few micrometers across, its magnetic domains aligned with the ancient field. Locked in place by the thermodynamics of cooling, surrounded now by calcium carbonate that has not moved or dissolved or been altered since the grain settled into the seafloor mud of the late Cretaceous. The compass is real, the alignment is real, the information it carries is real. It has been sitting in the dark, inside the rock, for 84 million years, pointing in a direction that records precisely what the Earth's field was doing and where, implicitly, the rock was sitting relative to the pole when the sediment settled. This is what we mean when we say the rock remembers, not that it chooses to preserve the past, not that it is performing some function analogous to the biological function of memory in a living brain. It means only that the physical state of the rock today is a consequence of the physical conditions that existed when the rock formed, and that the link between those conditions and that state is simple enough and stable enough that we can read backward from the state to the conditions. The rock is a record the way a fossil bone is a record, not because the bone decided to be preserved, but because the physics of permineralization happened to work in its favor, and we can read the chemistry and anatomy of the bone to reconstruct the biology of the living animal. The magnetic grain is the same. The chemistry of iron oxides happens to work in geology's favor, and we can read the orientation of the grain to reconstruct the orientation of the ancient field, and from that the ancient latitude. The honest thing to say, before leaving the fossil compass and turning toward the larger question it enables us to answer, is that the reading is not always simple, and the record is not always clean. Rocks can be remagnetized. If a rock is later heated above its Curie temperature by burial, by metamorphism, by the intrusion of a nearby magma body, its original magnetic record is erased and replaced by the new field direction at the time of reheating. If chemical changes in the rock form new magnetic minerals after the initial cooling, those new minerals will record the field at the time of their formation, not the time the rock first solidified, and the two records may be very different ages. If the rock has been physically tilted, folded, or rotated by subsequent tectonic deformation, the inclination you measure today is not the inclination at which the grains originally locked, and you have to correct for the deformation before you can extract the paleolatitude. These are the reasons paleomagnetic work requires large numbers of samples, statistical tests for consistency, and cross-checks against the geological context of each site. The Italian Scaglia Rossa is valued precisely because it does well on those tests. It has not been strongly metamorphosed. Its stratigraphy is well understood. The deformation it has undergone as it was folded into the Apennines can be corrected for using standard geometric methods. The magnetic minerals it contains are primary, meaning they formed when the sediment was first deposited, not later, and the record across the interval from 86 to 78 million years ago the Santonian and Campanian stages of the late Cretaceous, the age of Tyrannosaurus, and the last great inland sea of North America, is continuous, unbroken, and internally consistent in a way that gives the signal reliability. This is not a single anomalous measurement from a single outcrop. It is a pattern reproduced across multiple sites, in rock whose origin and history are well documented. And that pattern tells a story the limestone has been holding in patience since the dinosaurs were alive, waiting for someone to learn the language of frozen iron and come and listen. The story is simple for all its strangeness. The world leaned, not the plates sliding across one another, not the surface reshuffling its geography while the deeper earth stayed still. The whole solid earth, the entire mantle and crust shell from the surface down to the boundary of the fluid outer core, eased itself around its own unmoving axis, carrying every continent and every ocean basin simultaneously in the same direction by the same amount, rotating the whole assembly so that what had been positioned at one latitude slowly found itself at another. And then the same force, or its consequence, its counterpart, the physics of rebalance that is built into any spinning body that carries more mass in some directions than others, drew it back. The limestone recorded both the outbound lean and the return. It recorded them in the inclination of grains too small to see, and it preserved those inclinations through the death of the dinosaurs, through the emergence of mammals and then primates and then us, through every ice age and every interglacial, through the lifting of the Alps and the erosion of 10,000 landscapes that no longer exist, until a geologist's core bit pressed into an outcrop in the hills of central Italy in the early 21st century. And the sample was wrapped and labelled and carried to a laboratory where a magnetometer read the angle of the frozen grains, and a computer converted that angle to a latitude, and the latitude told the story. The story was, the Earth moved, not just its surface, the whole thing. And the rock knew, because the rock could not help but know. Because the physics of iron at high temperatures does not lie and does not forget, and does not change its story to fit a more comfortable version of events. This is why the fossil compass matters. Not merely as a scientific curiosity, not merely as a technical detail about how paleomagnetism works. It matters because without it, true polar wander would be undetectable. We would have no way of knowing whether the planet's solid shell had ever moved relative to its spin axis, because no human being has ever been alive long enough, or attentive enough, or equipped with instruments sensitive enough to watch it happen in real time. The only way to know the Earth has rolled is to find the memory of the rolling written in the rock. And the rock, without any intention or awareness, obliges, and so the question that remained. Once scientists understood that frozen iron in cooling rock could remember the direction and steepness of an ancient magnetic field, was a deceptively simple one. They had the mechanism. They had the tool. What they needed now was the patience and the nerve to take that tool and press it against the problem of whether the whole Earth had ever rolled. That work began in earnest in the 1950s, in the quiet way that most transformative science begins, not with a single dramatic announcement, but with the slow accumulation of measurements that refused to behave the way they were supposed to. Keith Runcorn was a physicist at Cambridge, methodical and deliberate in his approach, the kind of scientist who trusted data above theory, and who was. in the early part of the decade, engaged in a project that most of his colleagues considered peripheral at best. He was collecting measurements of paleomagnetism from rocks across Britain, plotting the ancient magnetic pole positions they implied, and trying to understand what the resulting track meant. The apparent polar wander path for Europe, the line that the poles seemed to have traced through geological time, as read from the rocks of a single continent, curved through the Pacific Ocean in a long wandering arc, retreating north through the Mesozoic and the Paleozoic until it converged on where the pole sits today. This was strange enough, but when Edward Irving, working in Australia, and P.M.S. Blackett, who had come to the problem from a distinguished career in nuclear physics and cosmic ray research, began compiling similar apparent polar wander paths for other continents, something stranger still emerged. The paths did not match. Not merely differed slightly, the way measurements from different laboratories sometimes differ. They were separated by thousands of kilometers, crossing one another, diverging in ways that had no obvious explanation if the pole had simply been wandering through space while the continents sat still beneath it. Think about what this means. If you photograph a moving object from two different windows of the same building, the photographs should show you the same motion. The object is the same. Space is the same, only the angle of view differs, and you can account for that. But if you photograph what you believe is the same moving object from two windows, and the object appears to be in a completely different place in each photograph, then one of two things must be true. Either you are not photographing the same object, or the windows themselves have moved. Runcorn and Irving and Blackett were photographing the same object. They were reading the position of Earth's magnetic pole as recorded in ancient rocks, and the same pole, at the same moment in geological time, appeared to be in two different places when read from two different continents. The logical conclusion, the only conclusion that made the measurements coherent, was that the windows had moved. The continents were not fixed. They had drifted, slowly, over hundreds of millions of years, carrying their magnetic records with them, and this was why the apparent polar wander paths diverged. This was, of course, one of the crucial pieces of evidence that eventually convinced the scientific community of what Alfred Wegener had argued with great persistence and rather poor reception decades earlier, that the continents were in motion. Wegener had come at the problem from a different direction, the shapes of coastlines that fit together like puzzle pieces. Coal deposits in the Arctic that spoke of ancient tropical forests, the traces of glaciers carved into rocks that now sit in the tropics, a whole archive of paleoclimate evidence suggesting that the land had once been somewhere else. He had the observation. He lacked a convincing mechanism, and without the mechanism the geological establishment was skeptical to the point of hostility. Paleomagnetism in the 1950s began to provide what Wegener's intuition had lacked, a rigorous, quantitative demonstration written in the rocks themselves that the continents had indeed moved. But here is where the story bends towards something deeper. Because when Runcorn and his contemporaries plotted the divergent apparent polar wander paths and subtracted out the motion of the continents relative to one another, when they corrected for drift and asked what was left, they found something. Not nothing. A residual signal, a motion that could not be explained by the continents moving apart from each other, a component that was shared, in the same rotational sense, by all the continents simultaneously. Something had moved that was not any individual continent. Something had moved all of them at once, in the same direction, by the same amount, around the same axis. That shared residual was true polar wander. The distinction is precise, and it is worth holding clearly in mind, because the history of popular accounts of this subject is littered with the confusion between the two. Plate tectonics is the story of individual lithospheric plates, the great slabs of crust and uppermost mantle that cover the Earth's surface like a cracked eggshell, moving independently of one another, driven by the pulling weight of cold, dense slabs sinking back into the mantle at subduction zones, and by the pushing pressure of new seafloor being created at mid-ocean ridges. The plates move relative to each other. Australia drifts north, India collides with Asia and raises the Himalayas. The Atlantic widens by roughly the thickness of a fingernail per year. Each plate has its own trajectory, its own speed, its own history. True polar wander is something else entirely. It is not the plates moving relative to each other. It is all of them, the whole coherent shell of mantle and crust together, rotating as one body over the fluid outer core in response to a shift in where the planet's mass is concentrated. The diagnostic test is this: plate tectonics produces different motions for different plates. True polar wander produces the same rotational motion for every plate simultaneously, all turning together around a single axis that lies on the equator. One motion is the independent shuffling of pieces. The other is the rotation of the whole puzzle at once, while the pieces stay arranged exactly as they were. It was Thomas Gold who gave this physical intuition its clearest early expression. Gold was a theorist of unusual breadth and occasional provocation, an Austrian-born British physicist who would go on to propose ideas about pulsars and the origin of natural gas that were considered heterodox by his contemporaries and vindicated, in part, by later work. In 1955, he published a paper in Nature with the calm and slightly alarming title, Instability of the Earth's Axis of Rotation. His argument was essentially this: any rotating body will tend to reorient itself so that its axis of maximum moment of inertia, the direction in which the most mass is distributed as far as possible from the center, lines up with the spin axis. This is because spinning with the most mass flung outward to the greatest distance is the configuration of lowest energy, and physical systems, given enough time and a pathway, tend toward lower energy. Gold illustrated this with an image that is remarkably easy to hold in the mind. Imagine a perfectly smooth spinning ball, perfectly uniform in its distribution of mass, spinning freely in space. It spins stably, with its axis fixed. Now place a small beetle on its surface. The beetle adds a tiny concentration of mass at one point on the ball. That mass is not at the equator, it is off-center relative to the spin axis. The ball, if it is free to reorient, will slowly roll until the beetle's added weight sits on the equatorial bulge, where centrifugal acceleration is greatest, where mass wants to be when a body is spinning. The ball rolls to balance itself. The beetle ends up on the equator, and if the beetle then crawls to a new position, the ball rolls again. Earth is the ball. The beetle is any concentration of mass that is not symmetrically disposed around the spin axis, and the crawling of the beetle is the geological process. The slow accumulation of a great lump of cold, dense, subducted material in the mantle, the rise of a vast superplume from the core-mantle boundary, the gradual growth of a large volcanic province that shifts the mass and triggers the reorientation. The whole planet rolls to put the new mass concentration where spinning wants it, somewhere near the equator, where centrifugal outward pull is strongest. But Gold's argument needed a critical refinement to match what actually happens on Earth, and that refinement involves the equatorial bulge itself. Earth is not a perfect sphere. Because it spins, the planet is flattened at the poles and swollen at the equator, bulging outward by a radius that is roughly 21 kilometers greater at the equator than at the poles. This is an enormous discrepancy in absolute terms, 21 kilometers of extra rock and ocean, girdling the entire planet. And this bulge is heavy. It represents an enormous concentration of mass spread around the equator, and it creates a gyroscopic resistance to reorientation, a stabilizing force that works against any tendency to roll. A planet with this bulge is not like a smooth, uniform ball. It is more like a spinning top that has been deliberately weighted along its equator to make it reluctant to tip. This is why the Earth does not simply respond to every small geological perturbation by immediately rolling. The bulge is the flywheel, the stabilizer, the conserving force that holds the current orientation against small shoves. True polar wander proceeds only when the mass redistribution in the planet's interior is large enough and sustained enough to overcome the stabilizing resistance of the bulge. And here is where the story adds a layer of complication that is both beautiful and slightly vertiginous. The bulge is not rigid. Over very long timescales, not the timescales of human history or of written civilization, or even of the whole span of our species on this planet, but geological timescales of millions of years, the mantle behaves as an extraordinarily viscous fluid. It flows, very slowly, with a viscosity that makes the thickest cold honey seem agile, but it flows nonetheless. And because it flows, the bulge is not permanent. If the whole Earth rolls even slightly, if the solid shell begins to reorient, bringing a new direction into alignment with the spin axis, the bulge, given enough time, will slowly relax and begin to rebuild itself around the new equatorial direction. This means that the flywheel is not fixed. The stabilizer gradually, over millions of years, adapts to the new orientation. As the planet rolls and the mantle flows, the bulge shrinks in the old direction and grows in the new one. This is called viscous readjustment, and it is the thing that allows true polar wander to proceed at all over geological time. Without it, the bulge would simply fight every reorientation forever, and the planet would never tip. With it, the bulge slowly yields, accommodating the roll, making the new orientation stable. But there is a subtlety even within that. The bulge does not readjust instantly, it lags behind. So as the planet begins to roll in response to a mass redistribution, the bulge is still partly reflecting the old orientation, creating what is sometimes called a fossil bulge, a memory of where the equator used to be, still pulling the planet back toward the old alignment, even as the new mass distribution is pulling it toward a new one. A fossil bulge creates a kind of elastic resistance in the middle of the motion. This is relevant to the Italian limestone and to the question of why the planet swung 12 degrees away and then came back. But that answer belongs a little further along. First, there was the problem of measurement. Even once scientists understood that something called true polar wander existed, that a component of apparent polar wander was shared by all continents simultaneously and represented a real rotation of the whole Earth, there was an immediate and vexing challenge. How do you distinguish it from plate tectonics? The continents are all moving all the time, each on its own path. When you look at the paleomagnetic record from a single continent, you see both the motion of that continent and any whole Earth rotation superimposed on top of one another. They are mixed together in a single signal, and separating them requires a reference frame. If you want to know whether a train is moving, you look at the station, But if the station is also moving, you need something else. Something truly fixed, or at least more fixed than the things you are trying to measure. In the Earth system, the chosen anchors are the deep-sourced volcanic hotspots, places like the chain of islands that forms Hawaii, where a persistent upwelling of unusually hot mantle material has been burning through the overlying plate for tens of millions of years, leaving a trail of progressively older volcanic islands and seamounts extending to the northwest as the Pacific Plate moved over it. The hotspot itself appears to be rooted so deeply in the mantle, far below the plate boundary level where most geological action occurs, that it moves only very slowly relative to the deep mantle as a whole. By treating a network of hotspots around the world as approximately fixed anchors, geologists can construct what is called a hotspot reference frame. They can track where the plates have moved relative to those anchors through time and subtract that motion out. What remains? The motion that cannot be explained by the plates moving over the hotspots is the motion of the whole solid Earth relative to the spin axis. That is the true polar wander signal, isolated at last from the geological noise. This is not a perfect technique. The hotspots do move slightly relative to one another, which means the reference frame is an approximation rather than an exact measurement. Scientists debate the degree to which hotspot motion contaminates the true polar wander signal, and the debate matters for the magnitudes that get reported. But the technique is good enough to see the signal, good enough to confirm that the whole Earth rotation is real and distinguishable from plate motion, good enough to begin measuring how large and how fast it has been. And what the hotspot reference frame showed, when applied carefully to the geological record of the last few 100 million years, was that the Earth had indeed rolled, had done so multiple times, had moved by amounts that varied depending on the time period and the quality of the data. Some proposed episodes of true polar wander were modest and well constrained. Others were dramatic and fiercely debated. The field had, by the early 21st century, established the reality of the phenomenon with considerable confidence, but was still arguing, productively, as science does, about the details. This is the context in which the study of the Scaglia Rossa limestone, published in 2021 in Nature Communications, arrived. The research was led by Ross Mitchell and Sarah Slotsnik, working with Joseph Kirschvink and colleagues. Kirschvink was a geobiologist at the California Institute of Technology who had spent much of his career thinking about paleomagnetism and its implications for Earth's deep history, and who had been involved in some of the most ambitious and most contested proposals about large, ancient polar wander events. Mitchell was a geologist with a particular interest in Earth's rotational history. Slotsnik brought expertise in the mineralogy and geochemistry of paleomagnetic records. Together they chose a target that was, in terms of age, well within the range where paleomagnetic data are usually reliable, and in terms of preservation, about as good as the geological record offers. The target was the late Cretaceous. Specifically, the window of time from roughly 86 million years ago to roughly 78 million years ago. A span of about 8 million years sitting squarely in the middle of the age of dinosaurs, after the massive marine reptiles and before the asteroid impact that ended that long chapter of Earth's history. This was the Santonian and Campanian stages of the geological timescale. A period when the global climate was warm and the shallow seas were full of the carbonate-secreting organisms whose remains would slowly accumulate into the pink limestone of the Scaglia Rossa. Pelagic limestone is in many ways an ideal material for this kind of study. It forms slowly, layer by layer, as the tiny shells of organisms drift down from the sunlit surface and settle on the seafloor. Each thin layer represents a small interval of time, perhaps thousands of years, perhaps tens of thousands. And as the carbonate sediment accumulates, magnetic grains within it align with the prevailing field direction before the sediment is compacted and eventually lithified into stone. The record is continuous, not punctuated by the gaps and unconformities that often interrupt other kinds of geological sequence. If you can read it carefully enough, a section of pelagic limestone is something close to a slow, quiet diary, page after page of the Earth's magnetic state and geographic position stretching back through millions of years. The outcrop in the Italian Apennines that Mitchell and Slotsnik and their colleagues sampled spans exactly this window, roughly 86 to 78 million years ago. And it is remarkable for how undisturbed it is, how continuous its record, how clearly the magnetic signal is preserved in the rock. They took cores from the outcrop, brought them to the laboratory, and measured the magnetic inclination at each sampled level. The inclination, that angle of dip, the steepness of the frozen needle relative to horizontal, is the number that converts directly to paleolatitude through the relationship that the tangent of the inclination equals twice the tangent of the latitude. They were not measuring direction to the pole, they were measuring how far from the pole the rock had been sitting when it formed. What they found, moving up through the sequence from 86 million years ago towards 78 million years ago, was a systematic change in inclination. The numbers shifted. The implied paleolatitude moved. Not by a small amount attributable to measurement error, not by the gradual few degrees that ordinary plate motion would predict for such a short interval of geological time, but by something considerably larger, a swing of roughly 12 degrees, outward from where the rock had been, and then, over the course of a few million years, a return. The inclination increased, held at its higher value for a time, and then decreased back toward where it had started. The rock had moved poleward by about 12 degrees of latitude and then moved back, not because the Italian plate had made a sudden detour and returned to its starting point, not because the plate had done anything unusual at all, but because the whole solid Earth, with Italy riding upon it, along with every other piece of continent and ocean floor, had rolled roughly 12 degrees relative to the spin axis, and then rolled back. The authors called this a cosmic yo-yo, and the image is apt. A yo-yo does not fall continuously downward, it reaches the end of its string and returns. Whatever drove the rolling outward, and we will come to what the evidence suggests was the driver, was counterbalanced by a restoring force that pulled the Earth back toward its previous orientation, so that the motion was not a permanent shift of 12 degrees, but a temporary excursion that the planet ultimately undid. This was significant for several reasons. It contradicted a claim that had appeared in the literature arguing that Earth's spin axis had been essentially stable, without significant true polar wander over the last 100 million years or so. The Scaglia Rossa data said otherwise. They said the planet had wobbled its whole self during a period that was geologically quite recent by the standards of true polar wander research, and that it had done so in a way that was oscillatory rather than directional. The Earth had not simply tipped to a new orientation and stayed there. It had oscillated, tipped and returned, like something pushed off balance and pulled back by a restoring spring. The restoring spring, in this case, is closely connected to the equatorial bulge and its fossil memory. As the planet begins to roll, The bulge, that 21-kilometer deep band of extra mass around the equator, starts to resist. But more than that, as the mantle slowly flows and the bulge begins to readjust toward the new equatorial direction, it simultaneously creates a memory of the old one, a gravitational pull back toward where the spin axis used to sit. The fossil bulge is the elastic component of the restoring force. It is the reason the planet does not simply roll to a new position and stay there permanently every time a geological event shifts the mantle's mass distribution. Think of it this way. If you push the rim of a spinning gyroscope gently sideways, it will precess, move in a direction perpendicular to the push, rather than simply tipping in the direction you pushed. A gyroscope resists being reoriented. The Earth's equatorial bulge behaves analogously, and the viscous relaxation of that bulge means the resistance is time-dependent. In the short term, the bulge fights the rolling. Over millions of years, as the bulge readjusts, some of the resistance fades and the rolling can proceed. But the fossil record of the old bulge orientation remains embedded in the mantle's density structure for a very long time, and it contributes a gravitational pull that can, under certain conditions, pull the planet back toward the old orientation. This is the mechanism that geophysicists believe is responsible for the oscillatory character of what the Italian limestone recorded. Something, and the most likely, something involves the redistribution of mass in the deep mantle, driven by the dynamics of mantle convection, pushed the planet's inertia axis slightly away from the spin axis around 86 million years ago. The planet began to roll in response to bring its inertia axis back into alignment with the spin axis. And for a few million years, the rock at what would become the Scaglia Rossa outcrop was drifting poleward, its magnetic grains recording steeper and steeper inclinations. And then, the restoring force of the fossil bulge, combined perhaps with a change in the mass redistribution itself, was sufficient to reverse the direction of roll. The planet swung back. The inclinations recorded in the limestone returned toward their starting values. The cosmic yo-yo completed its arc. 12 degrees may not sound like a great distance. On a human scale, it is perhaps the difference between the latitude of London and the latitude of Gibraltar, the difference between the grey skies and pale winters of northern Europe and the warmth and dryness of the Mediterranean coast. But these were not human distances. These were planetary distances, registered not by any living thing, but by the locked memories of iron grains in cooling limestone, preserved without distortion through 84 million years. And they were not the distances that any individual plate travelled, because every plate on Earth travelled the same 12 degrees, in the same direction, at the same time. As the whole mantle and crust shell rolled together, the entire surface of the planet shifted its relationship to the pole. Dinosaurs walked across the Cretaceous landscape without knowing they were 12 degrees closer to a pole than they had been before. Or perhaps, depending on where those landscapes were located, 12 degrees farther from one. The forests and the wetlands and the shallow seas adjusted their climates over the long arc of millions of years, as they always do, driven by the many forces that shape climate over geological time. The rolling of the whole Earth was not sudden. It was not violent. It was immeasurably slow by any standard other than the geological, a drift so gradual that nothing alive could perceive it. And yet the rock perceived it, the rock recorded it. And the record was still there to be read 84 million years later. by people with coring equipment and magnetometers and the mathematical tools to convert a frozen angle into a latitude and a latitude into a motion. What the 2021 study did, beyond providing a specific and well-constrained example of true polar wander in the late Cretaceous, was to reinforce a point that had been central to the field for decades, but was still sometimes lost in popular accounts. The Earth is not simply the passive stage on which plate tectonics performs. The Earth is itself in motion, in a second, deeper sense, rotating slowly within its own spin in response to the shifting of internal mass. The plates slide over the surface, and the surface, along with everything below it down to the outer core, very slowly rolls. The two motions are independent. A continent can be drifting north on its plate, while the whole planet simultaneously rolls in a way that pushes that same continent slightly south relative to the pole. The net motion is the combination of the two, and unraveling which motion is which requires exactly the kind of careful paleomagnetic work and reference frame analysis that the field developed over the second half of the 20th century and continues to refine. This is also why it is important, when thinking about true polar wander, to keep it rigorously separate from a third phenomenon that sometimes gets mixed in by accident. Geomagnetic reversals, the events in which Earth's magnetic field flips its polarity so that the needle of a compass that currently points north would instead point south, are something else entirely. A geomagnetic reversal changes the direction of the field, but moves nothing. The rocks stay where they are. The continents stay where they are. The planet stays in the same orientation relative to its spin axis. Only the field flips, driven by processes in the fluid outer core involving the convection and electrical currents that generate the geodynamo. True polar wander moves the solid Earth. Geomagnetic reversals flip the field that the solid Earth generates. They are related phenomena only in the sense that both are read from paleomagnetic data, but they are as different, mechanically, as a person turning their head and the compass in their pocket reversing its needle. Keeping these three phenomena separate, plate tectonics, moving the crustal plates independently, true polar wander rolling the whole solid Earth coherently, and geomagnetic reversals flipping the field without moving anything solid is not merely a matter of scientific precision. It is the thing that makes the story of the Scaglia Rossa limestone interpretable. The reason the Italian rocks record a 12-degree swing and return is not that the magnetic field reversed its direction. Reversals are geologically instantaneous, geomagnetically chaotic, and they leave a very different signature in the rock, not a smooth change in inclination, but a complex, often ambiguous change in the field's direction and intensity. The signal in the Scaglia Rossa is a smooth, systematic, coherent change in inclination that tracks latitude through 8 million years of geological time. That is not a reversal. That is the planet moving, and the planet's movement, as the Mitchell and Slotsnik and Kirschvink study made vivid, is not ancient history in any dismissive sense of that phrase. 84 million years ago, measured against the age of the Earth, is not even the last tenth of the story. The planet rolled within what is, geologically speaking, recent memory. And there are reasons, written in the deep structure of the mantle, to expect that it will roll again. To understand why the Earth rolled, and why it may roll again, you have to go somewhere most people never think about, the very bottom of the mantle, a boundary layer 2,900 kilometers beneath your feet, where the slow rocky world above meets the liquid iron world below. It is a surface of extraordinary strangeness. The rock of the lower mantle, pressing down from above with the weight of nearly the entire planet, meets the churning liquid outer core from below. And the temperature at that interface is estimated to be something in the range of 4,000 degrees Celsius, hotter than the surface of the sun. Nothing alive, nothing constructed, nothing human has ever been within any meaningful fraction of that distance. We know it exists, and we know something of what resides there, only because of the same seismic waves that carry the news of earthquakes around the globe. When an earthquake large enough to shake the whole planet occurs, it sends pressure waves and shear waves radiating outward in every direction, through every layer of the earth, and the way those waves speed up or slow down or bend or reflect tells seismologists about the material through which they passed. Dense, cold rock conducts seismic energy faster. Hot, buoyant, partially different composition rock conducts it more slowly. And when geologists assembled the records of thousands of earthquakes, recorded at hundreds of seismic stations distributed across the globe, and inverted all of that information into a three-dimensional picture of the mantle's interior, a technique called seismic tomography, which does for the Earth's interior something like what a medical CT scan does for a human body, they found something unexpected sitting on the core-mantle boundary. Two structures, enormous ones, each roughly the size of a continent, stretching across thousands of kilometers of latitude and longitude and rising several hundred kilometers to perhaps 1,000 kilometers off the core floor into the lower mantle above. They were identified by the fact that seismic shear waves slow down conspicuously as they pass through them, which is why their formal name is Large Low Shear Velocity Provinces, or LLSVPs. One of them sits roughly beneath the African continent and the Atlantic. The other sits beneath the Pacific Ocean. Informally, among the researchers who study them, they have been given names. The one beneath Africa is called Tuzo, after the Canadian geophysicist J. Tuzo Wilson, who was among the founders of plate tectonic theory. The one beneath the Pacific is called Jason, after Jason Morgan, the American geophysicist who helped formalize the theory of plate motion. These are not whimsical labels. They are a way of acknowledging that these two vast, anomalous structures at the base of the mantle are real enough and significant enough to deserve names. What exactly Tuzo and Jason are made of is still debated. They may be ancient oceanic crust that subducted into the mantle hundreds of millions of years ago and settled to the bottom rather than mixing thoroughly with the surrounding rock. They may be primordial material left over from the early Earth, chemically distinct from the convecting mantle above. They may be some combination of both. Their exact composition remains a live research question. What is not debated is that they are there, that they are large, and that because they are large, because they have a composition and temperature different from the surrounding mantle rock, they perturb the distribution of mass within the Earth. And mass distribution, as we have now spent considerable time understanding, is the engine of true polar wonder. Think of what it means to have two continent-sized bodies sitting asymmetrically on the core-mantle boundary. The Earth's mantle as a whole is not perfectly uniform. It is not a smooth, homogeneous shell of rock surrounding a liquid core. It has regions of differing density, differing temperature, differing composition, and the two LLSVPs are among the most dramatic of those variations. Their presence means that the figure axis, the direction of the Earth's maximum moment of inertia, the direction in which the greatest concentration of mass lies, is not perfectly aligned with the spin axis. Not necessarily. The figure axis is influenced by the distribution of mass throughout the whole mantle volume, and any significant departure from perfect spherical symmetry that is not also perfectly symmetric about the spin axis will create a mismatch. That mismatch is the seed of true polar wander. Because the Earth, like any rotating body, has a tendency, a deep, physical tendency rooted in the mechanics of angular momentum to align its spin axis with the direction of maximum moment of inertia. When those two things diverge, the solid Earth reorients to bring them back into agreement. The spin axis in space stays fixed, the solid body rolls to meet it. And Tuzo and Jason, sitting lopsided and vast on the core floor, are among the forces that can create and sustain that divergence. But they are not the only ones. The mantle is not static. It convects. Hot material rises from the core-mantle boundary in great columns and plumes, carrying heat upward over millions and millions of years. Cold material, former ocean floor, former oceanic crust, the leading edges of lithospheric plates that have slipped beneath other plates at subduction zones and are now sinking back into the mantle under their own weight, descends from the surface. These subducting slabs are dense and cold, and as they sink, they carry mass downward into the interior. As they arrive in the lower mantle and accumulate, they shift the planet's mass distribution. A thick cluster of subducted slab material, settling in one region of the deep mantle over tens of millions of years, constitutes a genuine change in the moment of inertia axis. The kind of change that triggers a reorientation. Rising plumes from the base of the mantle do the same thing in reverse. A superplume, a particularly large and vigorous column of hot material rising from near the core-mantle boundary, possibly from the edges of one of the LLSVPs, can carry buoyant, low-density material upward, reducing the mass in that part of the deep mantle and redistributing it. The effect on the moment of inertia axis is real and calculable, at least in principle, and it accumulates over geological time. Every subducting slab, every rising plume, every episode of large-scale volcanism that draws from or feeds back into the deep mantle is, in a small way, adjusting the balance of this planet's spinning top. Over tens of millions of years, those small adjustments can sum to something substantial. This is the slow mechanism behind the Scaglia Rossa limestone's testimony. Whatever process, whatever redistribution of deep mantle mass, whether driven by a shifting subduction regime, a change in the geometry of convection, or some reorganization near the core-mantle boundary, was responsible for the true polar wander event approximately 84 million years ago. It operated over millions of years. It moved the figure axis away from the spin axis by something on the order of 12 degrees. The solid Earth responded by rolling, gradually, to rebalance. The pink limestone in the Italian Apennines, cooling quietly on the floor of a Cretaceous sea, recorded the planet's inclination as it moved, logged the outward swing, and then recorded the return. The cosmic yo-yo that Ross Mitchell, Sarah Slotsnik, Joseph Kirschvink, and their colleagues identified in the rock's frozen magnetic memory. Why did it swing back? This is the question the Scaglia Rossa data raises with particular force. The planet did not keep rolling in one direction. It went out and returned. The answer almost certainly lies in the relationship between the figure axis and the equatorial bulge, that 21-kilometer excess of radius around the planet's middle. The gyroscopic flywheel that stabilizes Earth's orientation. The bulge is not rigid. Over geological time, the mantle flows, and the bulge slowly relaxes and rebuilds around whatever equator the planet is actually spinning around at any given moment. But it does not do so instantaneously. It lags, it has memory. And that memory, sometimes called the fossil bulge, the lingering imprint of the old equatorial excess that has not yet fully adjusted to the new orientation, acts as a restoring force, a slow gravitational pull, drawing the solid Earth back toward its previous position. If the mass perturbation that drove the initial 12-degree tilt was itself temporary, if a subducting slab finished its descent, or a plume reorganized, or whatever deep process created the imbalance then eased, the fossil bulge would pull the solid Earth back. Not instantly, not dramatically. Over millions of years, the same kind of slow, viscous flowing that allowed the bulge to begin relaxing in the new direction would now relax it back, and the planet would oscillate. It would swing out and swing back, and perhaps settle close to where it had been. The yo-yo is, in this interpretation, not a mystery, but the expected behavior of a system with two competing forces, the drive to realign the figure axis with the spin axis, and the conservative, memory-laden drag of a bulge that has not yet forgotten where the old equator was. The 84-million-year episode is, importantly, not the largest true polar wander event in the geological record. It is simply one of the better constrained ones. And the history of the science includes a far more dramatic claim, one that is worth knowing about and worth holding with appropriate care. Near the boundary between the Precambrian and the Cambrian period, approximately 530 million years ago, something remarkable happened. The fossil record, which had been dominated for billions of years by microbial life and simple soft-bodied organisms, suddenly, in geological terms, erupted into a diversity of complex animal forms, phyla appearing in the space of a few tens of millions of years that would persist and diversify into all of the major animal lineages we recognize today. This is the Cambrian explosion. Its causes have been debated for as long as the phenomenon has been recognized, and many hypotheses have been advanced. Changing ocean chemistry, rising oxygen levels, the development of predation as an ecological force, chance contingencies in evolutionary history. All of these explanations address things intrinsic to the biosphere. Joseph Kirschvink, one of the scientists whose name appears on the 2021 Scaglia Rossa study, along with Robert Ripperdam and J. Ross Evans, proposed in the 1990s a hypothesis of a very different kind. They suggested that near the Cambrian boundary, the Earth may have experienced a form of true polar wander so extreme, so fast, by geological standards, and so large in amplitude, as to constitute a fundamentally different kind of event. The technical name for this is inertial interchange true polar wander, or ITPUBL. The physics behind it turns on what happens when the three principal moments of inertia of a rotating body, the maximum, the intermediate, and the minimum, become nearly equal in two of their values and then shift their relative ranking. When the intermediate and maximum moments of inertia approach each other and then exchange places, the body can reorient by up to 90 degrees relatively rapidly. The mathematics of rotating bodies allows for this. It is not impossible in principle. Kirschvink, Ripperdam and Evans argued from paleomagnetic and geological data that something of this kind had in fact occurred around 530 million years ago. The Earth may have rolled, under this hypothesis, by something approaching 90 degrees, equatorial regions sweeping toward the poles, polar regions swinging toward the equator, over a geologically short interval. And they suggested, speculatively, that such a dramatic and rapid reorientation of the solid planet would have changed ocean circulation, altered climate zones, disrupted habitats in ways that could have been a trigger or an amplifier of the explosion of animal diversity in the fossil record. Ecology reshuffled overnight in geological terms, by the planet itself rolling under every ecosystem simultaneously. It is a striking idea, and it must be held as exactly what it is, a documented hypothesis, actively contested, not a settled consensus. The paleomagnetic data from the Cambrian boundary are among the most difficult to interpret in the entire geological record. The rocks from that period have been through hundreds of millions of years of subsequent geological history, burial, heating, chemical alteration, the overprinting of later magnetic signals onto earlier ones. The problem of separating primary magnetization, the original frozen field direction, from all the secondary magnetizations acquired since, is genuinely hard. And critics of the IPW hypothesis have argued that some of the paleomagnetic signals being interpreted as a 90-degree polar wander are contaminated, misstated, or otherwise unreliable. The debate is real, technical, and ongoing among specialists. The modest 12-degree oscillation at 84 million years ago, recorded in the clean, well-studied pelagic limestone of the Apennines, is far more tightly constrained than any Cambrian-era claim. The Cambrian hypothesis is something to hold in mind as a genuine scientific possibility, an illustration of how dramatic true polar wander could in principle become, not as an established fact about what the Earth has done. What is established, and what carries no meaningful controversy, is that some degree of true polar wander has occurred throughout Earth's history, is occurring now, and will continue. The present-day motion of the pole is measurable with the precision of modern space geodesy, GPS networks, very long baseline interferometry, satellite laser ranging, and it confirms what the physics predicts. The geographic North Pole, the point on the Earth's surface that lies directly beneath the spin axis, has been drifting. Its motion over the 20th century was on the order of 10 centimeters per year, a rate that seems negligibly small, but which, sustained over millions of years, is the pace at which the 84-million-year event unfolded. The present pole drift is not ancient geology. It is happening, and something changed around the year 2000. The direction in which the pole had been slowly drifting broadly toward Canada through most of the 20th century shifted. The pole began drifting in a different direction. Researchers tracking this change identified the cause, and it is instructive precisely because it is the same physics operating at a scale we can watch in real time. The shift in drift direction around 2000 was driven largely by the redistribution of water mass on the Earth's surface, melting ice sheets in Greenland and Antarctica, removing enormous quantities of ice from the poles and releasing that water into the world's oceans. The depletion of groundwater aquifers on the continents, particularly in Asia and North America, as human civilization has drawn down ancient underground reservoirs at rates far exceeding their natural recharge. Mass is moving. The planet's moment of inertia axis is shifting in response. The solid Earth is nudging itself infinitesimally toward a new balance. The direction of pole drift changes. This is not alarming. The magnitude of the present-day effect is tiny, centimeters per year, not degrees per million years as in the ancient events. And the cause, in this case, is predominantly human rather than deep mantle dynamics. But it is a live demonstration of the principle. You do not have to take the existence of true polar wander on faith, grounded in abstract physics and ancient rock. You can watch the pole move. You can see the drift direction shift. The same force that tipped the planet 12 degrees 84 million years ago is operating right now, in miniature. Driven not by continent-sized blobs on the core-mantle boundary, but by the comparatively mundane processes of melting glaciers and depleted aquifers. The Earth is a physical body obeying physical laws, and those laws do not switch off between geological epochs. This planet is not alone in exhibiting such behavior. There are, in the solar system, other worlds where the same kind of reorientation is written into the landscape, and their existence is a reminder that what happened to the Earth is not some singular anomaly, but an expression of a process that any rocky or icy body with the right internal structure and the right distribution of mass can undergo. Mars carries the most dramatic example. On the surface of Mars, in its western hemisphere, sits a volcanic plateau of extraordinary scale. Tharsis is, by some estimates, the largest volcanic structure in the solar system, a region roughly the size of North America, elevated several kilometers above the surrounding terrain, built up over billions of years by successive volcanic eruptions that added layer upon layer of basaltic rock. The mass of Tharsis is so immense and so asymmetrically placed relative to Mars's spin axis that planetary scientists have calculated it must have substantially changed Mars's moment of inertia axis from whatever position it occupied before Tharsis grew to its present size. The planet responded the way physics demands. It reoriented. Mars rolled not its spin axis in space, but its solid body relative to that axis to bring Tharsis closer to the equator, where the rotational bulge accommodates excess mass most efficiently. The evidence for this Martian reorientation is written in features on the surface. Ancient shorelines proposed to mark former ocean margins, patterns of volcanic and tectonic activity. The distribution of polar ice deposits, whether Mars once had a large ocean, and whether the evidence for one is as clear as some researchers argue, remains debated. But the Tharsis-driven reorientation itself is among the more broadly accepted ideas in Martian geophysics. A world built an enormous volcanic structure over billions of years, and the weight of that structure slowly rolled the planet beneath it. The physics is the same as for Earth. Only the cause, volcanic construction, rather than deep mantle mass anomaly, differs. On the moons of the outer solar system, evidence of a related phenomenon appears in a different form. Enceladus, the small icy moon of Saturn, whose south pole vents plumes of water vapor into space through dramatic geysers, shows surface features that researchers have interpreted as the signature of a polar wander event. Not the solid mantle and crust rolling over a liquid core, as in Earth's case, but the icy outer shell of the moon rolling relative to its interior. Europa, the ice-covered moon of Jupiter, shows similarly suggestive surface patterns. These icy bodies have a decoupled structure, a hard outer shell floating, in effect, on a liquid layer beneath, and if the mass distribution of the outer shell becomes sufficiently asymmetric, that shell can roll independently. The mechanism is related to, but not identical with, the true polar wander of a rocky planet. It is rather an illustration of how widely the basic principle applies. Any rotating body carrying an asymmetric load will tend to reorient to bring the excess mass toward the equator. The universe, it seems, rolls. And this brings us, at last, to something that must be said clearly, because it is the most common confusion that attaches itself to the subject of polar wander in popular accounts. There is a persistent and genuinely old idea circulating in certain corners of popular culture and the broader landscape of alternative history that the Earth's crust has undergone sudden, catastrophic displacements, that the poles have shifted, not over millions of years, but over days or weeks, that continents have lurched to new positions in geological instants, that ancient civilizations were destroyed by such an event. This idea has had various champions over the decades. The American writer Charles Hapgood promoted a version of it in the mid-20th century, calling it Earth crust displacement, and attracted the endorsement for a time of Albert Einstein before the geological community examined the hypothesis and found it physically untenable. The idea has never gone away entirely. It surfaces periodically in books, in documentary films, on internet forums, attached to various dates and predictions and claims of suppressed knowledge. It is not supported by the evidence. Not because scientists are incurious or closed-minded, but because the physical constraints on how fast the solid Earth can reorient are real and severe. The equatorial bulge, that 21-kilometre excess of radius around the planet's middle, is not a passive feature. It is a gyroscopic stabilizer of extraordinary inertia. For the solid Earth to reorient by tens of degrees in days or weeks, it would have to overcome the angular momentum of the bulge essentially instantaneously, which would require forces of a magnitude that simply do not exist in the Earth system or in any known astronomical process on the relevant timescale. The mantle flows, but it flows slowly, its effective viscosity over the timescales relevant to true polar wander is immense. A sudden crust slip of the kind Hapgood described would require the mantle to behave on a timescale of days as if it were water. It does not. It behaves as what it is, rock that flows only over millions of years. The geological record shows no evidence of such an event. The stratigraphic sequence of sedimentary rocks laid down through time does not record the global disruption that a rapid, large-amplitude polar shift would produce. The paleomagnetic record does not show it. The fossil record does not show it. The 12-degree oscillation in the Scaglia Rossa limestone, unfolding over millions of years, is the kind of reorientation the Earth actually undergoes. The 90-degree Cambrian event, contested and debated by specialists, would have unfolded over geologically short but still substantial intervals, not years, not centuries, but millions of years. The catastrophist pole shift narrative is a story that has been told many times, and it is not this story. This story is slower, quieter, and in the end more astonishing for being true. What is true is large enough. Let it settle for a moment. The entire solid Earth, the mantle, the crust, every mountain range and ocean trench and continental shelf is not fixed in position relative to the planet's spin axis. It rolls. It reorients slowly over millions of years, driven by the slow redistribution of mass in the deep interior. Two continent-sized structures, Tuzo and Jason, sit on the core-mantle boundary right now, lopsided and immense, exerting their quiet gravitational influence on the balance of a spinning world. Cold slabs of former ocean floor are sinking into the mantle at this moment along subduction zones in the Pacific and elsewhere, adding their mass to the deep interior in ways that will, over geological time, shift the figure axis by some small amount. Hot material is rising from near those same anomalous boundary structures in plumes, carrying buoyancy upward, redistributing mass in the other direction. The planet is in motion, not just at the surface, where plates slide and collide and mountains rise and erode, but throughout its entire volume, a slow thermal and gravitational churning that has never stopped since the Earth accreted from the solar nebula 4.5 billion years ago. And in the rocks, the memory of all that motion is preserved. Not perfectly, not everywhere, not without ambiguity and the need for careful interpretation and the honest acknowledgement that some signals have been overprinted or corrupted or are still contested by the specialists who read them. But in places, in particularly well-preserved, well-studied sequences of sedimentary and igneous rock. In the pink pelagic limestone of the Apennines, laid down layer by patient layer on a Cretaceous seafloor, the record is clear enough to read. The inclination of frozen magnetite grains, tiny as dust, records the latitude at which they formed. The systematic change in inclination through 8 million years of the late Cretaceous records the planet's motion. Not the motion of a continent over a fixed mantle, not the reversal of a magnetic field, the motion of the whole Earth, rolling through 12 degrees of arc and returning. We know this because Keith Runcorn and Irving and P.M.S. Blackett, in the patient laboratory work of the 1950s, established that rocks could honestly record ancient magnetic fields and that apparent polar wander paths diverged between continents in ways that proved the continents had moved. We know it because Thomas Gold, in 1955, in a short and elegant paper in Nature, worked out the physics of a rotating body reorienting toward its maximum moment of inertia, and illustrated it with the image of a beetle crawling on a spinning ball, adding weight to one spot, rolling the whole ball to fling that weight outward to the equator. We know it because the development of seismic tomography gave us eyes in the deep mantle and revealed Tuzo and Jason on the core-mantle boundary, continent-sized mass anomalies sitting where no one had previously had reason to look. And we know it because Ross Mitchell and Sarah Slotsnik and Joseph Kirschvink carried samples of pink limestone out of the Italian Apennines, measured the magnetic inclination frozen into those samples with the precision that modern instruments allow, corrected for the motion of the Eurasian plate using the accumulated knowledge of decades of paleomagnetic work, and found, in the residual signal, the unmistakable signature of the whole planet rolling and returning around 84 million years ago. None of these people were looking for the same thing. Runcorn and Irving and Blackett were trying to understand why continents seemed to have moved. Gold was a physicist thinking about the mechanics of rotation. The tomographers who mapped Tuzo and Jason were trying to understand mantle convection and the sources of volcanic hotspots. Mitchell and Slotsnik and Kirschvink were testing a specific claim about the stability of the Earth's spin axis in the late Cretaceous. Science does not always proceed by a single grand design. It proceeds by many hands working in many places, and the picture of true polar wonder that we now possess is the assembled product of all of them. It is, when you set it out in its full shape, a remarkable thing to have learned. That the planet has a hidden kind of motion, distinct from the drift of continents and distinct from the reversal of its magnetic field. That this motion is recorded faithfully and quietly in the magnetic memory of ordinary rock. That two enormous structures on the core-mantle boundary, structures that no human has seen, that we know only through the mathematics of seismic waves, are among the engines of that motion. that the pole is drifting right now, at this moment, its direction nudged most recently by the weight of melting glaciers and depleted aquifers, the same physics that tipped the planet 12 degrees 84 million years ago, working at a scale small enough to be attributed partly to human hands. And it is, just as importantly, a calm thing. There is no alarm in it. The timescales are so vast, the process so gradual, so deeply embedded in the slow viscous behavior of rock that flows only over millions of years, that no part of this story calls for anything other than wonder. The planet rolls at a pace that makes the growth of mountain ranges seem hurried. The evidence it has left in the rock is quiet, almost shy. A slight change in the angle at which iron grains froze in cooling stone, a deviation in inclination that has to be extracted from decades of geological work before it speaks clearly. But it does speak. The Scaglia Rossa limestone speaks, the frozen magnetite grains, 100 times smaller than the width of a human hair, each one a tiny compass needle that locked in place as the temperature dropped below 580 degrees Celsius in a lava flow, or settled through warm Cretaceous water onto a seafloor that is now mountain rock in Italy, they speak. They say, the planet moved. Not the continents sliding over the mantle. Not the magnetic field reversing its polarity. The planet itself. The whole solid Earth rolling to rebalance itself around a spin axis that stayed, all the while, fixed in the indifferent emptiness of space. That is what we learned. That is what the pink limestone recorded, and what the careful work of scientists over decades allowed us to read. The Earth rolled. It rolled back. And somewhere beneath your feet, 2,900 kilometers down, where rock meets liquid iron at temperatures hotter than the sun's surface, the slow redistribution of mass continues. Tuzo and Jason sit lopsided in the dark, enormous and ancient. Slabs of cold former seafloor are descending, adding their weight to the deep interior. The moment of inertia axis drifts by amounts too small to measure in a human lifetime, but real. The planet is paying attention to its own balance. It always has been. And the rock remembers. Whatever remains of the questions you carried into this hour, whether the Earth could really roll, and whether anyone could possibly know, you have the answer now. Not a simple answer, not a tidy one, but an honest one, grounded in real places and real measurements and the real, careful, contested, ongoing work of people who spent their careers listening to what stone has to say. The answer is yes. It rolled. It rolls. And the record it left is as permanent as the rock itself. History will still be here in the morning. For now, rest.